Installing mental model for HTTPS. Right now, your browser is sending data across the internet. Passwords, credit card numbers, private messages, and by default, the internet doesn't encrypt any of it. HTTP, the protocol that powers the web, sends everything in plain text. Your login form, the username and password fly across the wire as readable characters. Anyone sitting between you and the server can see them, and anyone isn't hypothetical. Your coffee shop Wi-Fi, every device on that network can see your traffic. Your ISP, they can read every page you visit. A compromised router along the way. Same thing. It's like mailing a postcard. Anyone who handles it can read it. And your data passes through dozens of hands on its way across the internet. This is the problem HTTPS was built to solve. That S stands for secure, and it works by adding a layer called TLS, Transport Layer Security, between your browser and the server. But before any encrypted data can flow, something remarkable has to happen first. Your browser and the server need to agree on a shared secret over a public channel where anyone could be listening. How do you share a secret when everyone is watching? It starts with a handshake, and the choreography is beautiful. Your browser sends a client hello. This is a greeting that says, here are the encryption methods I support. Here's a random number I just generated, and here's my key share. All of this travels in the clear. Anyone watching can see it. The server responds with a server hello. It picks the strongest encryption both sides support, sends its own random number and key share, and attaches its certificate. The certificate is proof of identity. It's how your browser knows it's really talking to your bank, and not someone pretending to be your bank. Now here's where it gets clever. Both sides sent key shares. These are based on something called Diffie-Hellman. Each side generated a private number they never share. But by combining their private number with the other side's public key share, they both arrive at the same secret, without ever transmitting that secret. Watch that again. Each side has a piece. They exchange public pieces. And mathematically, both sides compute the same shared secret. An eavesdropper sees the public pieces, but can't derive the secret from them. In TLS 1.3, this entire handshake completes in a single round trip. One message out, one message back, and both sides have a shared encryption key. Everything after this point is encrypted. But wait, the server sent a certificate. How does your browser know that certificate is legitimate? Certificates are signed. When a website wants HTTPS, it goes to a certificate authority, a trusted organization that verifies identity. The CA checks that you actually own the domain, then signs your certificate with their private key. Your browser has a built-in list of trusted root CAs, about 150 of them. Companies like DigiCert, Let's Encrypt, and Google Trust Services. Their public keys are baked into your operating system and browser. But root CAs don't sign website certificates directly. That would be too risky. If a root CA's signing key were compromised, everything it ever signed becomes suspect. Instead, there's a chain. The root CA signs an intermediate CA certificate. The intermediate CA signs your website's certificate. Your browser receives the website cert and the intermediate cert. It walks the chain upward. Does the intermediate cert verify the website cert? Does the root cert verify the intermediate? Is the root cert in my trusted list? If every link checks out, the certificate is trusted. If any link fails, your browser shows a warning. This chain of trust is what the entire HTTPS ecosystem is built on. Billions of connections per day, all anchored to a handful of root certificates stored on your device. So why not just encrypt everything with the key pair from the certificate? The server has a private key. The browser has the public key from the certificate. Why not use that? Because asymmetric encryption is slow, really slow. It involves massive prime numbers and modular exponentiation. Encrypting a single web page with RSA would take roughly 1,000 times longer than symmetric encryption. Symmetric encryption, algorithms like AES, is fast, blazing fast. Modern CPUs have dedicated AES hardware instructions. They can encrypt gigabytes per second. But symmetric encryption has a problem. Both sides need the same key, and you can't just send a key over an unencrypted channel. This is why HTTPS uses both. Asymmetric cryptography to establish the shared secret, symmetric cryptography for the actual data. The handshake uses Diffie-Hellman, which is asymmetric math, to derive a shared secret. From that shared secret, Both sides generate identical symmetric session keys, and from that point forward, everything is AES. It's a relay race. Asymmetric runs the first 100 meters, establishes the secret. Then it hands the baton to symmetric, which sprints the remaining marathon. Fast, efficient, and secure. And those session keys? They're unique to this connection. Even if someone records your entire encrypted session and later steals the server's private key, they still can't decrypt the traffic. That's called forward secrecy. So, what does the encryption actually look like in practice? Once the handshake is done, your browser wraps every message in a TLS record. The payload, your actual HTTP request, gets encrypted with AES using the session key. An authentication tag gets appended. This tag proves the message hasn't been tampered with. Then the encrypted record flies across the internet. The server receives it, decrypts with the same session key, verifies the authentication tag, and processes your request. The response gets encrypted the same way and sent back. To anyone intercepting the traffic, the data is gibberish. They can see that you connected to a server. They can see the size of the packets. But the contents? Unreadable. Your passwords, your messages, your credit card numbers. All of it is just noise to the eavesdropper. And this happens seamlessly. Every HTTP request and response gets wrapped and unwrapped. Your browser does it automatically. The server does it automatically. You never see any of it. The only visible sign is that tiny padlock icon in your address bar. And about that padlock, it might not mean what you think it means. The padlock means your connection is encrypted. That's it. It does not mean the website is safe. A phishing site can have HTTPS. A malware distribution site can have HTTPS. Certificate authorities don't verify whether a website is trustworthy. They verify whether you own the domain. And getting a certificate is free and takes about 30 seconds with Let's Encrypt. So a site called mybankloginsecure.com can get a certificate, display the padlock, and look perfectly legitimate. The connection is encrypted, nobody can eavesdrop. But the person on the other end is a thief. HTTPS protects the channel, not the destination. It's the difference between a locked mailbox and a trustworthy post office. The lock keeps your mail private, but it doesn't tell you who's reading it on the other end. And there are limits. HTTPS doesn't hide which server you're connecting to. The domain name is visible during the handshake, though TLS 1.3 encrypts more of it. HTTPS doesn't prevent the server itself from logging your data, and it doesn't protect against vulnerabilities in the website's code. HTTPS is essential. The internet would be unusable without it, but it's one layer of security, not the only layer. Cognitive architecture, updated.